All right, earlier in the chapter, we referred to the entropy of the universe increasing with any spontaneous reaction, right? But let's talk about what does that mean. Okay, so the universe is everything, including the system that we are interested in, which is basically where the reaction is happening, plus the surroundings. The surrounding is everything around our system. So obviously, if we combine the system and its surroundings, that's basically saying everything or the universe. So remember that the entropy change of the universe is greater than zero for a spontaneous reaction. However, that change in the universe is a sum of the change in the entropy of our system, which again is what a reaction is, the change in the entropy of our particular reactants and products. But there's also an associated change in the entropy of the surroundings. What we're going to be talking about here in the next few slides is how to calculate the entropy change of the surroundings. We already discussed in the previous slides how to calculate the entropy associated with our particular reactions by utilizing the equation of products minus reactants, utilizing the data from Appendix A2, right? So now we're going to calculate the entropy change for our surroundings. Again, just to recapitulate, the system is the part that we are interested in, our reactants and our products, our reaction system. The surroundings is everything else. All right, continuing with the same equation, we can see immediately that the entropy change of the universe will be positive if both of these terms are positive, meaning if we have an entropy increase for the system and also an entropy increase for the surroundings, or alternatively, if the entropy change for the system is negative but is offset by an increase or a really large change in the entropy of the surroundings. Alternatively, if the entropy of the surroundings, if the change in the entropy of the surroundings is negative, meaning that we cause an increase in the order of the surroundings, then it has to be a really large delta S for the system, a really huge increase in the disorder for the particular system in order for that to make it a spontaneous process where the delta S of the universe is greater than zero. All right, so how do we calculate the entropy for the surroundings, the entropy change? For an isothermal process, which is a process that doesn't cause a temperature change in the surroundings, then we can calculate the delta S for the surroundings utilizing this equation, where we have negative Q of the system. Q is the heat associated with the system. So Q is basically how much heat was gained or lost in a particular was gained or lost by the system in a particular reaction or phase change. And that's going to be divided by the temperature in degrees Kelvin, the temperature at which that change or that chemical reaction happened. So notice that we're utilizing the the value of the energy or the heat associated with the system, but we're multiplying it by a negative sign to indicate that that system is basically losing energy to the surroundings or gaining energy from the surroundings. So the opposite of what happens to the system happens to the surroundings. That's why that negative sign is there. Similarly, we can change this equation into an enthalpy term if that process occurs at a constant temperature, because enthalpy is basically heat associated with a process at a constant pressure. So the equation basically becomes that the entropy change for our surroundings is going to be equal to the negative of the enthalpy change of the system divided by the temperature. The enthalpy change of the system is something that we can utilize, that we can calculate by utilizing the equation of products minus reactants, because this is basically the enthalpy of the reaction. Or this can be actually the enthalpy associated with a phase change particularly. I go ahead and let you know that there's very good examples on the book. See these two numbers for practice. All right, the entropy change with a phase change. So notice that now from the previous page, we were calculating the entropy change for the surroundings. In this slide, I'm asking you, or I'm showing you how to calculate the entropy change for the system if you have a phase change as opposed to a chemical reaction, right? So a phase change means that you have, let's say, water, which is changing from solid to liquid. So still water. It hasn't changed to any other chemical compound or molecule, right? So it's just a phase change. So to calculate the entropy change for the system, we're going to take the heat associated with that particular change divided by the temperature. Here it says heat Q reversible. Reversible because a phase change is a reversible change, right? And we can also calculate it as the enthalpy change for that phase change divided by the temperature in degrees Kelvin. Now, here on the bottom right, I'm showing just a plot of temperature versus entropy. Remember that at the phase changes, melting or boiling, the temperature actually doesn't change. You might remember that from early in the semester. But in this class, we said that the entropy does change significantly when you change from a solid to a liquid, and you can see that happening here. And it changes even more when you change from a liquid to a gas, because remember that you are increasing the level of disorder as you go from solid to liquid and then liquid to gas. And the gain is much bigger here from liquid to gas because now you are going from a liquid of specific volume to a gas that can expand to fill the container, and where the molecules are much farther apart from one another and have significant mobility. All right. From there now, just to remind you, these are the names of the changes in state. And in addition to that, I'm also showing you which ones have an entropy change for the system that is greater than 0, which is going to be the fusion or melting, which is going from solid to liquid, from liquid to gas, or even from solid to gas, which is sublimation. And then an entropy change of the system that is less than 0 would be the opposite processes: condensation, freezing, or deposition. All right, so now how do we calculate the free energy under non-standard conditions? We already know that for standard conditions, we can utilize the tables that contain the data and use the products minus the reactants, right? Or we could have used the equation that said that the delta G0 is equal to the delta H0 minus T times the delta S0. But what if we are not at standard conditions? What if the temperature is different? What if our partial pressures are not 1 atmosphere? What if our concentrations are not 1 molar? Then in that case, we're going to have to use one of two equations. One of the equations is shown on this slide. The next one is on the next slide. So for this particular slide, for this particular equation, is basically that we're going to use a very similar equation where we're going to utilize the enthalpy change at standard conditions and the entropy change at standard conditions, but we're going to change the temperature to whatever other temperature we are working at. That is not 298 Kelvin. And we can do this because the enthalpy change and the entropy change do change with temperature, but they change very little. And so that means that the error associated with utilizing them at a different temperature is not going to be that great. And so we basically can utilize the same equation with the enthalpy and the entropy at standard conditions, even if our temperature is not at standard condition. And just to point out, there is one example and one practice problem in the book utilizing this equation. Next, the next equation. If we have a different set of pressures or concentrations, this would be the equation to utilize. Basically, what it says is that the Gibbs free energy under non-standard conditions is going to be equal to the Gibbs free energy at standard conditions plus this term that basically allows us to have a different temperature as well as a different set of pressures or concentrations. Because remember that standard conditions had pressures of 1 atmosphere or concentrations of 1 molar. So if you have something other than that, then that needs to come here on this Q. So what is that Q? That Q is the reaction quotient, which remember is calculated just like an equilibrium equation. That reaction quotient was basically equal to our products divided by our concentration, the concentration or pressures of our products divided by the concentration or concentrations or pressures of our reactants, with each of them raised to their own coefficients. You guys remember how to do that, right? And it can be either in terms of pressures or in terms of concentrations, as I mentioned. Uh, so basically what we're saying again is that we can calculate the Gibbs free energy at standard conditions, and utilizing this term, we're basically correcting it for the right conditions for a particular problem. One thing that I want to warn you about this equation is that the units of R, which is 8.314 joules per mole Kelvin, which is your gas constant, those units are not typically going to match with the units of the Gibbs free energy at standard conditions, which is typically in kilojoules per mole. And so you really need to be really careful and make sure that you work with your units so that you either change the delta G into joules by multiplying the number by 1,000, or you change the value of the gas constant by dividing it by 1,000 in order to make it kilojoules per mole Kelvin. So that's very important that you convert your units, okay? So that your delta G and your R are on the same. For temperature, remember that we're always going to utilize degrees Kelvin. And again, there are more examples on your book. I will be doing a couple of problems with this here, but just to point out that there is more practice and more problems in case that you're still a little bit unsure about what we're doing. All right, so now we mentioned earlier on that the Gibbs free energy change is equal to 0 at equilibrium, because at that point your system is kind of not changing in that the concentration of the reactants and the products is basically set, right? We also know that at equilibrium, the value of the equilibrium constant is equal to your reaction quotient. So we can take the equation that we had in the previous slide and said, okay, at equilibrium, my delta G is going to be equal to 0. At equilibrium, my Q is equal to K, the equilibrium constant. And so now that I have this equation, I can actually solve for my delta G0 in terms of the equilibrium constant. So this equation right here is really important because it allows us to calculate or to predict, I should say, it allows us to predict the spontaneity of a system by utilizing the equilibrium constant for that particular reaction. That equilibrium constant could be that for any reaction. It could be a Ka for an acid dissociation. It could be a Kb for a weak base dissociation. It could be a Ksp for a solubility product problem where you have a solid. It could be Kw for water. It could be Kc or Kp. It doesn't matter. Any of those equilibrium constant numbers could go here, and it would enable you to predict the delta G. So here what I want to look at is what happens if my K, my equilibrium constant, is greater than 1. If the K is greater than 1, that means that my products are present in higher concentration than my reactants, right? And notice that that gives you a delta G that is negative. That means that systems in which your K is greater than 1 are going to be spontaneous. Now, if the K is equal to 1, that natural log of 1 is equal to 0, and so that means that the delta G is equal to 0. That means that now we're our Gibbs free energy change at standard conditions is going to be equal to 0. That's all. And finally, if the K is less than 1, then your delta G at standard conditions is going to be greater than 0, which means that at standard conditions, you're going to not have a spontaneous system. All right, another way to look at free energy and equilibrium is graphically here. So what we have is free energy on the y-axis, and then on the x-axis what we have is kind of the states of the reaction. Initially, I'm starting with just reactants, and as I continue, I actually start decreasing the amount of free energy. And this is a spontaneous process in the same way that a ball rolling down a hill is going to be spontaneous. Now, if I had started from this other side where I only have products, it is actually also spontaneous for the reaction to go backwards until we reach equilibrium. Equilibrium is here at the center. At equilibrium, we actually have the lowest energy situation, the most stable situation, and that's where your delta G is equal to 0. This is where your Q, or reaction quotient, is equal to K. Now, if I'm starting here on this side, that's where Q, or the reaction quotient, is less than K. When that is the case, we already know that the reaction is going to spontaneously continue to the right until it reaches equilibrium. That's something that we had said in earlier chapters. At the same time, we already knew that if Q was greater than K, we had too much product. And so the spontaneous thing for that reaction was to start utilizing the products to make more reactants so as to reach equilibrium. So that's spontaneous. The opposite, like if you're at equilibrium, for the reaction to go in this direction, to make more reactant, that would not be spontaneous. And similarly, if you're starting here at equilibrium, it would not be spontaneous for the reaction to all of a sudden make more products. Of course, here when we're talking about this, we're saying we're not changing the conditions, because we already know that if we change the conditions, if we change the temperature, if we change the pressure, we can actually affect the equilibrium. We can cause a shift in the equilibrium to basically a new equilibrium. All right, we already said that we have an equation, delta G equal to negative RT ln K, that allows us to relate the equilibrium constant to the Gibbs free energy change at standard conditions. Now we can solve that equation for K by basically first dividing both sides by negative RT, which is what I have done here. And then to get rid of the natural log, we can put both sides to e to the power of e. So what we get in the equation is finally that K, or our equilibrium constant, is equal to e to the power of this whole thing, negative delta G0 divided by RT, where the delta G0 is your Gibbs free energy change at standard conditions, R is 8.314 joules per mole Kelvin, and the temperature is in degree Kelvin. Another word of warning again, that you need to make sure that your units agree. With the R being in joules per mole Kelvin, your delta G0 will need to be in joules per mole. There are additional examples that I would recommend that you look at, and I'm pretty sure that this is 18.12 for the problem for your book. Sorry. All right, let's go ahead and do an example. So calculate the free energy delta G for a reaction containing 1.750 atmospheres of NO2 and 0.5 atmospheres of dinitrogen tetroxide. Okay, so we have basically two different pressures that are not 1 atmosphere. That means that we are not at standard conditions, because standard conditions would be 1 atmosphere for the partial pressures of each of those molecules, right? And the temperature, on the other hand, is at standard conditions, but that's too late because we are already not at standard conditions. All right, in addition to that information, we were also given the chemical reaction, and we are provided with the Gibbs free energy change at standard conditions for the two substances. Of course, remember that these things are things that you can find from a table. I don't actually have to give them to you. You have to know that you will be able to find them for pretty much any reactant and any product. All right, so how are we going to deal with this? Well, we said in the previous slide that we could calculate the Gibbs free energy at not standard conditions by utilizing the equation that says that the delta G is going to be equal to the delta G at standard conditions plus RT times ln Q. Right, so that's the equation that we're going to utilize. So how are we going to get this actually done? We don't have pretty much anything that we need yet. So the first thing, let's look at this delta G0. This is something that we can calculate from this information by using the equation of products minus reactants, right? And so we will do that. Let's think about what else do we need. R is a constant, temperature we have it, so those two we have. Now Q is a reaction quotient. The reaction quotient is something that we can calculate in terms of pressures by utilizing the pressures that we have here and putting in the equation that says that Q is equal to our products over reactants, with each of them raised to their coefficients. We'll get to that in a second, but let's start by calculating the delta G at standard conditions, and I'm gonna go ahead and do that down here. So my delta G at standard conditions is going to be equal to, I'm going to start with my products, okay? So product has a coefficient of 1. You don't necessarily have to type it, but I'm just doing it there so that you have your notes. Then I'm going to multiply it by the delta G naught for the N2O4, which is 98.28, and that's kilojoules per mole. Since I don't have any other product, I'm going to go ahead and close my bracket, and to that I'm going to subtract my reactants. I only have one reactant and it has a coefficient of 2, and then its Gibbs free energy change, or delta G, is equal to 51.84 kilojoules per mole. Close my bracket since I don't have any more, and now I'm ready to go ahead and put it into a calculator, and that gave me negative 5. Come on, let me type. 0.400. I need 4 significant figures according to this, and that is in the units of kilojoules per mole. And again, that's a 5.400. All right, I'm gonna leave it at that for now. Now, I'm going to go and calculate my reaction quotient, or Q, and for that I need to be able to look at my equation. So remember that Q is calculated in the same exact way as your K, where you do products over reactants. In this case, my product is going to be the N2O4. And remember that the information that they gave us was in pressure, not concentrations. So I'm going to go ahead and put that the pressure of N2O4, that's going to be just like that, not raised to any power because my coefficient is 1. But that is going to be divided by my reactants, where my reactant is going to be the pressure of NO2 raised to the power of 2. That 2 is because of the coefficient of 2 here. That's my equation for my reaction quotient. Now I have to go back and look at what pressures were given to me. So for the N2O4, what we have is 0.500 atmospheres. And for the NO2, what I have is 1.750 atmospheres. Don't like that the points don't show up. And once you plug that in, I'm sorry, I forgot my squared. Oops, squared, don't forget the squared. Once you do that, you get that the value of Q is equal to 0.163. And now I'm almost ready to plug everything in. So before I go and plug everything in, I'm going to remember that my R right here is 8.314 joules per mole Kelvin. Joules per mole Kelvin. And it turns out that the delta G that I calculated here is in kilojoules per mole Kelvin. They are not in agreement, joules versus kilojoules. So what I'm going to do is that I'm going to convert this one to joules by multiplying by 1,000. So this gives me negative 5,400 joules per mole. All right, and I think now I'm ready to begin. Oh wait, one last thing, my temperature. I cannot just plug 25 degrees Celsius. I need to have it in degrees Kelvin. By adding 273, that gives me 298 Kelvin. Okay, now I'm ready to substitute. So my equation said, let me go up a little bit. It says that my delta G is going to be equal to that my delta G0, which is negative 5,400 joules per mole, plus my value of R, which is 8.314 joules per mole Kelvin, times the temperature, which is 298 Kelvin, times the natural log of Q, where Q is 0.163. And once you plug everything in, you end up with delta G being equal to, not zero, delta G being equal to negative 9,894. Wait, four significant figures, I think. And actually, I need just, yeah, I'm just going to leave it like that, joules per mole. We are done with that problem. And now, the last problem. All right, so it says, determine the Gibbs free energy change in kilojoules per mole for the aqueous dissociation of nitrous acid, HNO2, at 298 degree Kelvin. The Ka for HNO2 is 4.0 times 10 to the minus 4. All right, so remember that we had an equation that related K's, the equilibrium constants, to the value of the Gibbs free energy, which is our delta G. That equation was that delta G at standard conditions was equal to negative RT times ln K. And remember that I mentioned that that K could be any K. It could be a Ka, it could be a KSP, it could be a KW, KB, whatever. Any of the Ks. Right, the next thing that I want us to think about, are we at standard conditions? Well, according to the only information that we have available, we are. This is the temperature being 298 Kelvin, we are at standard conditions. Great. And so we can actually just go ahead and plug in. So here I'm going to have the equal to negative for that negative, then R, which is 8.314 joules per mole Kelvin, times the temperature, which is 298 Kelvin, times the natural log of K, where I have run out of space, so I'm going to move my ln. I'm going to put multiplication times ln of K, which is 4.0 times 10 to the minus 4. And once you plug that in, you should get delta G0 is equal to, let's see. I got 1.938, and that's times 10 to the 4. And the units were joules per mole. Notice that I have joules in this case because once the K's cancel away, and actually, yeah, the Kelvin is the only thing that cancels away. So what I have is joules per mole. What I need to give this in is kilojoules per mole according to the problem. So to convert from joules to kilojoules, we basically divide by 1000, which means that the delta G0 is going to be equal to 1.93. Come on, let me write, please. Nope, doesn't want to. Okay, let's do it really slowly. 3. Okay, that looks much better. 1.938 times 10 to the 1, and that's in joules per mole. Or I could also write it without scientific notation if it lets me write. Nah, it doesn't want to write. So I'm just going to tell you that you could also write it as 19.38 joules per kilojoules per mole. Sorry, kilojoules per mole. Okay, it's letting me write now. 19.38 kilojoules per mole. The end. That is it for this chapter. Have a great day, guys. Bye.